So, oops. Sampling. Resampling. So think of like image scaling first. Like for example, you have a large image and it's too big, then I want to scale it down so it's like fit into the screen. Then I scale it like it's very kind of like intuitive operation. How do you scale it down? The simplest thing, yeah, the simplest thing is just remove some pixel, right? For example, like if I have a downsampling like 2 times by a factor of 2, I would just say every odd samples, every odd columns, and every odd rows, I would just remove that, right? So if I do downsampling like this, after downsampling, I just try to upsample back. So basically, like just zooming back in the sense that maybe I get a bigger, each of the pixel have, instead of like one patch, I can make a 2x2, 4x4, or even maybe get a filter of that, just moving it out. But that's basically what I had like here, like after downsampling and upsampling. What you can see is like it doesn't look too bad, but also doesn't look too good. But when we downsample, we don't care about like if we are not careful. There's always some of these pretty weird situation. Like the last one is not so apparent, but this one, of course, you can see that. Like if you downsample without any careful consideration, that's what we will get. So do you know why I will get that? Like that's a technical term for that. Anyone have like? Yeah, yes. I'm impressed. You seem to know everything. So okay. So this is an example. Like another example is pretty bad also. But what is aliasing? Okay, look at this one also. This one I want to show you just because not just in the middle, like you can see some aliasing, but also like this is another illusion, kind of cool illusion. Can I point out what's the illusion here? Do have you guys see this before? You know? So you know also? No, not exactly that. Like, there's some also like perception illusion, vision perception illusion here going on. Actually, the green, how do you call that? Like spiral is different from. I mean, it's the same color as this blue spiral. The two are same color. You probably don't believe it. So when you zoom in, it's more apparent that it still looks a bit different, but like if you kind of box some part of that, it's indeed actually same color. So okay, it's a digression, but anyway, like why do we have like aliasing? This is another illustration. Like if I go down like 256. Continue to do like one, I mean 2 times downsample multiple times, eventually you get like really weird, like 16 by 16 like this. Aliasing. So remember that like last time we showed that video, like the helicopter is like what's that called? It's not spinning. What do we call that thing? Propeller. Okay. How about that? Is that a fan or like how? Anyway, it doesn't matter. So I guess it's the timing problem, right? So you have, for example, if I have this sinusoidal function, if I sample, this is my sampling time here. Depends on how I sample, I can get like wave different like kind of like wave their interpretation there. So I can think of like okay, instead of like have this frequency, I can have much lower frequency. And I guess we kind of mentioned like Shannon sampling, that is basically if you have a signal of like a certain frequency, like with a bandwidth up to like f max. So if you want to retain that signal, you need to sample at least 2 times that frequency. Do you guys remember that? Some of this in cell processing. Actually, this probably is a good illustration, like why you will need that 2 times sampling, or like you will need to have sufficient rate of sampling. Like if your sampling rate is too low, like this one, like this illustration here, you have this original image. Let's say I sample like at this points here, then I will get back the patterns. It's like 4 back pixel, 4 white pixel, and so on, right? It's a good sampling here. This one is good also, but this one, okay, maybe this one will get all black, right? So if I sample like too low, I only sample it here, 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 I will get all black here. So if I sample here, also we have back kind of bad sampling here. Is I have black here, white, and so on and so forth. So I will have like 1 back pixel and 2 white, and then like 2 white and 4 back there. So but of course we talk about frequency interpretation. If basically what happened in frequency interpretation, don't worry if you haven't taken any cell processing. So if I have like this is like the frequency domain here, this is just a 1D signal. So like this is a frequency kind of like the magnitude there, just the amplitude. And so if I sample that, like let's say I sample at a rate, this is every TS second, then I will have, basically this will be just repeating every 2 pi of the omega. And okay, this is repeating, like I guess we mentioned that last time. Why is this kind of like exactly repeating here? This is okay. Of course, we said. Let me. This is kind of difficult. Or maybe I draw something. So if a frequency band here, so if I sample, then basically what happened, it will be repeating at higher frequency, basically, essentially, have something like that. So I'll say, wait, intuitively, why I'm repeating? So one thing I can think of is like, if I'm sampling that, like let's say this is like the frequency axis here, somehow you of course I can normalize that. Therefore, like I have the unit is like every 2 pi and so on, right? Every 2 pi minus 2 pi and so on. So what I'm saying, like once you sample, then you lost information, right? You don't have any information beyond certain frequency, right? So therefore, like must be you won't have like anything left, something, right? But my question is like, can I have like nothing there? Like, what I mean is like, since you sample, like maybe you have something like at the beginning, have something outside, but because you have sampled it at a particular weight, you essentially just dump away some information, right? So therefore, like beyond somewhere, maybe here is 2 pi, but beyond somewhere, you know that you don't have any information anymore. So you need to fill in that information. So that's 2 options there. One option is like, okay, intuitive 2 options. One is like basically completely blank, right? So outside high frequency it's all blank. Another possibility is like this, like it was just repeating itself, right? Repeating. And if you, I won't go into that, but if you look at the equation, it basically is repeating, right? Because I have like the frequency is just 2 pi omega t, right? I don't have 2 pi actually. J omega t, right? Sorry, this is E here. This looks so ugly. So if I have like, it will be like And of course, like because the exponential function is repeating, so therefore, like if I have omega like 2 pi more, it will be just repeating itself. So now this is like if I have nothing, then I sample. I mean, I shouldn't say nothing. If I have continuous function, then I sample. I have like repeating the frequency band like this. And then apparently, if my sampling rate is too low, then I will start to repeating in earlier. So I will be something like this. So then this will, in effect, cause the aliasing, right? That's the what. And then like so this is like from continuous to discrete signal, right? How about I start with discrete signal? If I have like let's say originally already discrete. So for example, like remember like we have this discrete Fourier transform that have basically 2 pi what k and xn, let's say. This is my Fourier transform for frequency k, right? So remember that like this is a basically for 1D signal of length n, or you can think of like the signal actually repeating itself like every with a period n. Then so therefore like the frequency band basically is like every n sample here 0 and will repeating itself, right? So I have signal like this. Maybe I start with like the original frequency is like this. So if I do a downsampling, now a downsampling I will have my signal originally like is a n samples, right? Now it will go down to just n over 2 samples, right? And then in the frequency domain also like from n sample, I will just go to n over 2 sample. So similar to what we had earlier, essentially we also what happened again? So yes, it will go down bolder and spread like this. Basically, this will like half time, short time like this. So therefore, like it only when okay, this one actually I can't exaggerate a bit like this. Oh, I think it's okay. So then like what should I do? Like I want to avoid this aliasing, right? So what should I do? Like if I want to downsample it.
If I increase the number of samples?
Yes, but what we are going on, like let's say we start with the image, like remember that in the first line where we have the big image, we still want to go down to a smaller image. So definitely our samples will get fewer, right? So maybe we start with 100 now to 50 by 50. But it's same as like what Brandon said, right? You want to have like more samples, like it's true, like, but I really want to have like this icon, tiny icon, right? So like I start with like a huge kind of big image, like 100 by 100. I go down to 50 by 50. So I know that like I probably have some aliasing here. Yes, what is that?
That's defining like that period for the signal.
So I think are you talking about doing a low pass filter for that? It's kind of like no. Okay. So yeah, here I guess if you really want to have this tiny image, of course what you're saying is that like okay, don't do this tiny image because you will get like bad aliasing. But if you really want to do that, like what you should do is like I would rather not to have this aliasing here happening like this. So therefore, like I would just truncate here somewhere, right? If I don't have this tail, then at least like this tail won't kind of get into this part of this frequency, right? So therefore, what I want to do is I want to just cut this tail off, like cut this tail off. Then essentially it's just a low pass filter, right? So I'll just try to do a low pass filter, and then after low pass filter, I can do the sampling. Yeah. So that's what happened really. That's what you do. Like if I do a low pass filter before I do that, so of course it's still like not good, right? But at least it keep kind of that pattern there. Doesn't like just create another new pattern, basically. So and for the original image is also like a little bit better than like what we had like earlier. So now this is like downsampling. So how about upsampling? So upsampling is just the opposite, right? So therefore, like upsampling should be what? Yeah. So it was just like just the opposite, right? So I have. So okay, let's see. If I have sampling, now go back to here. This is like the frequency. Like I have n samples here, 0 and so. In the frequency domain, I will repeat my signal, right? I have something like that. So if I do it 2 times upsampling, so what do I mean by 2 times upsampling will be like this? So basically, I have like n signal here, like maybe just 4 signal here, 4 points here, n equal to 4. So I have like this. Oh, this is big. Should I see like this? Maybe I just draw like this. Okay. So I have 4 values here. Now if I upsample, I will just fill in some zeros. So then I will go to like 2n. So this is too long. So it's like 2n is 8 now. So I will just say maybe the first one put this one here, and then this one move to here, and then this one move to here, and so on. And in between them, I will just set it to 0, let's say. So then for this subsampling, what do you expect for the frequency representation? What does it look like for the frequency domain? Do you know?
It's gonna grow tall and slim.
I think it's gonna go into the moon,
Okay. Many answers here. So you said go slim?
Yeah.
Go slim. So yeah, this goes slim, and then what?
Goes taller.
Yes. How about other places? How other frequencies? So Israel said like that.
No. From the top it's going to be like this, and then
Oh, like that?
no, but there should be like a straight line on the top, like it should be like
Fatter?
draw a straight line like horizontal line.
Or something like?
Yeah, and then like two lines.
Good eye.
Something like that.
Oh, okay, but this will be similar to this one, right?
It'll be in the inverted version of it because you have to apply like a bend filter and fix it. So
Oh, okay. Yes. But not that. Let's say just this operation. So, just for this operation, for this upsampling operation times 2. So from like, let's say n equal to 4 to n equal to 8. Now what happened to this frequency representation here? Actually, visually is kind of white, but how about the other frequency? So here you say it's go up like this, right?
The
But
other frequency would just like
wait. That not applying filter yet. So just this operation, and what will happen? So
You'll get like repeated like small triangles for each period.
yes. Oh, wait a sec. I probably don't want to join in the same, or maybe I can join in the same port here. But let me make sure that like I want to. Okay. Let me draw here. Like I use 2n now. So because now it's like repeating 2n sample every 2n samples, right?
So inside like that, like one of the triangles will have 2 little triangles.
2 or okay. Like that, right?
But that's like in the same period of one triangle. Like, yeah. But
Oh, okay, yeah. This is the correct one. So basically, like you can think of like here, like you go to up to this 2n here, right? This part just change the whole segment here, just change to here somehow, right? That's actually in the sense it doesn't look like any changes, but yeah, but okay. But it does. It does actually. It does. Because now the signal is supposed to repeating every 2n instead of repeating every n sample, and this is actually is again like some of this aliasing here that you don't want. So therefore, like essentially we'll do the same thing. We want to do a filtering. We can again like do a low pass filter again. We'll just like get away like all this. But now it's in the opposite order. In the earlier one, when we downsample, we first apply filter and then we downsample. This one we just opposite that. Like we first upsample and then like apply filter. So actually, if you upsample and apply a filter, in particular have a perfect filter. So this is a perfect filter, right? Perfect low pass filter. Do you remember what's the time domain representation for the perfect low pass filter? What signal you do a Fourier transform, you get a kind of like rectangular block. I think someone answered me last time. Yes, you think. Yes. You have a sink. Okay. You have, remember your, actually the Fourier transform is essentially symmetric. Actually, it's essentially symmetric. Only the basis, say here, like we use EJ by convention, you Fourier transform, you use a convention EJ kn over n, something like to pick when you transform from spatial domain to frequency domain. But then in a sense, like, you can also think of like from frequency domain to spatial domain, you're basically projecting to basis like e minus jk pi 2 pi over n, something like that. And of course, like, this minus sign doesn't do anything. So actually the transform itself is symmetric. So therefore, like, I think maybe some of you remember if you have a square signal, if you do a Fourier transform, you get a sinc function. Therefore, the reverse is true as well. So if you have in frequency domain, it's like that. In the time domain, it's basically the same function. So therefore, one way to think of this is like, you can have a perfect reconstruction if everything is ideal. Will be like you have this signal, just or like after you upsampling, you just like apply a sync filter to that. But that is like very hard to control the same filter. So actually, I guess in practice probably people will do something else. So but that is like in theory is a kind of perfect reconstruction. So therefore that's what we talk about. Like if we kind of upsample like that. Okay, I can skip this. So this is basically we just talk about it. So if we if we upsample that, like we have basically insert a kind of like a seals like between every sample, then basically we have this signal will have like kind of an aliasing part here, component here, so we can like filter that out and basically just apply low pass filter, and sync will be kind of an ideal reconstruction in theory. So but you can do something else. For example, if you have a kind of a triangular kind of like filter, that's essentially wait, is that a triangular? It's not triangular filter, I'm sorry. It's common if you use it's a triangular filter, but it's not in the frequency domain triangular filter. But if the filter like in the spatial domain is triangular, you are just doing a linear interpolation. So just like linear interpolate 2 points. So you have 2 points there. You just take the average between the two to fill in the middle, or you can do a Gaussian reconstruction. That's what we just mentioned. This is like in images, because you have like 2 dimensions, right? So you can linear one side, another linear one side. Then you have like the filter is like a tan. It's like called a bilinear interpolation. And also like bicubic is common choice, but I don't remember this way. So but yeah, you can find that it's a function. You can do a bicubic interpolation.
What do you mean by it?
Which one?
What is that function? Is it like how the function of the filter will
Yes, the filter in the spatial domain is like this.
Okay.
Yeah. So yeah. So it's like it's actually, maybe this gives a better illustration. So because in 1D, if your filter is just like a triangle, then yeah, it's basically, yeah. So therefore, like if you are 2D, you will have something like a tan. Yeah. So this is just a illustration here. So bilinear interpolation, you get something like that. This is just a Lewis label. It doesn't look good. Right? Your pixel just make it 10 times bigger. So this one using bicubic interpolation.
What's the difference between the bicubic and the Gaussian?
It's different. I don't remember the formula. I'm sorry, it's so tiny. You need to look at the slide. So it's basically a cubic interpolation. So a polynomial interpolation.
I mean, I feel like they give us the same result at the end. So when do we need to use like one and not the other?
Honestly, I guess many times we'll just use bilinear because it doesn't look too bad. This kind of like upsampling is not like super resolution. Now, if you really want to get tiny detail, then this won't work. Like anyway, you will get some blurry result anyway. So therefore, like it's just for visually just want to be appealing. So therefore, like yeah, I think like very common like just use bicubic or bilinear. Yeah. And this is okay. So if you do resampling, so therefore if you want to resample the image, then what you can do is like first upsample and then downsample again, right? If you resample to any kind of combination of resolution, then of course for upsampling you need to do filter after doing upsampling, right? And then downsampling you should do filter before downsampling, right? So essentially you can combine these two filters. So you can upsample, then filter, and then downsample. So okay, this is something like very simple, and I want to illustrate that like for your homework, like if some of you already finished that actually, that's a kind of like I'm not sure how. I mean, if you look at this illustration here. Oops. So why is that? So okay. So what do you see? What do you see? Anyone? Yes. So you can recognize both.
See Raymond Monroe whenever it's small and Einstein whenever it's larger.
Yeah. So can you explain like why you see that like at this moment? Like can you have a conjecture for that? Like why?
I think it's mainly because of the Aliasing is so in the middle, like when you're like, I can't tell if you're upscaling or downscaling in the middle. So we lost some information in the middle, but it gave us like the base of how we can construct Einstein's picture.
The Einstein's picture had defined edges, and once it got downscaled, those edges disappeared. So you kind of got new edges from the downscaled blurred image.
Yeah. Edges are high frequency. Yeah.
It might be a white filter, like white linear filter that we did at the end of Einstein's.
Yes. So when you do the filter, you get the low frequency. So essentially, you are in the actually. This is an example like how you get that. It's like you combining high frequency and low frequency images. So you put a image, basically do a high frequency filter for that image, and then I combine with another image, just a low frequency component of that part. When you combine together, so depend on the distance, you essentially like this is like actually what's going on, because human is like kind of, this is hard to see, but relatively speaking, this is a chat. It's called Campbell-Watson like sensitivity curve. So I don't know, what do you see? Like this is trying to show like basically here say what's showing here is like this chart is showing that like down there when I go down the y-axis it's something like it's more high contrast here, right? When you go up like higher y value here, the contrast keep decreasing. And of course you see like the x-axis you just have like different spatial frequency, right? So typically, I don't know what you see. It's like typically this is like what people can distinguish the difference for different contrasts. So if you have like different spatial frequency, when you have a really high frequency, our ability to distinguish contrast decrease. And also the same for like we have a low frequency. So we have a sweet spot somehow that's somewhere in the middle that like we are kind of more sensitive of contrast. So that's what's going on. When you change this distance, what does it change? Essentially, it's also changing the frequency of what you're looking at, right? The spatial frequency. So you are actually moving the sweet spot there. So therefore, like when you are moving, okay, like zoom in or moving farther away, your sweet spot like kind of moving to, I don't know, more on this low frequency side, right? Because now you say everything is looks like, yeah. So it's like if you're moving away and moving on this side here, moving to this side here, so therefore you see the low frequency component. I mean, if you move to this side here, you're more like closer. Then your sweet spot move to this side, you're kind of like have better contrast for high frequency component. So yeah, this is interesting. Like people didn't realize that like until like pretty late, basically. Yeah. So I quickly also talk about something else. Oh yeah, questions. I guess no questions. Typically, when I ask questions, no one have questions. So but I think you guys don't have questions. So here it's just I want to, because we are talking about sampling, also give a very quick introduction for pyramid. So image pyramid. It's just a very intuitive, like when you want to process video images. One widely used technique or trick is that you may try to process it in different resolutions. So what you can do is that you start with the original resolution, then you downsample it like for different levels, like 2 times, 4 times, 8 times, and so on. Then you try to like go down to like lower resolution and you sample there. For example, you want to try to look for something. Maybe you just like downsample like to lower resolution, then you see if you spot that, and then like when you spot something, you go back up to a higher resolution, and then try to figure out more detail and so on. Or like you can basically like do a pyramid and have all resolutions and try to recognize something in every resolution, because it depends on the distance, right? Maybe I try to look for a dog. The dog can be like closer to me or like can be farther away. So therefore I need to really, but it's hard to create a filter like to have different sizes, right? Maybe I keep just looking at the same size, but I just try to kind of process for different resolution. So the pyramid, of course, is very simple, right? Typically what we do is that we bury it and then downsample, bury it and downsample again and again. So this is called the Gaussian pyramid, and I also want to just quickly mention the Laplace pyramid. The Laplace pyramid is like after you have the Gaussian pyramid. So the convention is like the original resolutions, we call it G0. So we downsample, get G1 and G2 and so on. Then the Laplace pyramid is just like you take the difference of your current resolution Gaussian pyramid by the approximate from your high resolution. I mean the approximation from, it's hard to say. Like it's easy to look at the equation here. It's obvious, right? So basically, like I have G0, I keep downsampling as G1, G2, and so on, right? Then I have the approximate version G1 is like lower resolution than G0, so it's like half resolution of G0. Then I get approximation of G0 by upsampling this guy. Of course, I upsample also do some filtering there. So then I just basically subtract this G0 with the approximate version of G0, and I get L0, something like that. So we call it Laplace pyramid. I'm going to keep doing that, then I have different levels there. We call this a Laplace pyramid. So one very simple application is compression. It won't be the best compression, or it's actually a very bad compression. So it's a paper in the 80s, but just give you as an example application. So idea is that you just do compute the Laplace pyramid, and the Laplace pyramid, then you can each level you just kind of quantize and co-compress that. So it's very similar to JPEG compression as we mentioned last time. So your Laplace pyramid is like the high frequency component, right? So therefore you can kind of like we are less sensitive to that, so we can use a larger quantization step size, then we can compress that with Huffman coding and so on. And decoding is that after we have the Laplace pyramid, Of course, we can recover that back to the Gaussian pyramid, right? It's so hard for me to pronounce. So anyway, then you get G2, G1, G0 back, and G0 is just the original way. So that's actually more interesting application is like image compositing. Actually, I made it as a homework last time. I'm not sure I should make a homework again like this time, but maybe or maybe not because you have this another one. So very simple idea. You have this two images, let's say, where you can create a Laplace pyramid for both images. Then you just combine each level of the pyramid. Like one half take this apple, like one half take apple, another half take orange, and then like you just recover that back. So then you have a pretty nice blending there. So okay, that's all I have basically. So maybe like I showed. Oh, okay. First thing before I forgot is I set a lottery for presentation. So this for this kind of lottery, I hope that like can have some kind of delay. It would be pretty nice, but it's always you click and then it just give me the table right away. So okay, this is the order. So which you're early. So Robert also is early. He's here. Okay, then three guys on toast. Let's see. I make sure I make the day. Okay, yeah, this is okay. And Logan. Logan is are you here, Logan? Oh, you're Logan. Okay. Yes. So that's I will post the kind of up there also. So okay, maybe before I leave, like this give me. Okay, I also like the solution is here for the homework. So, but so I'm not sure I'm making this homework too easy. So maybe next time not that much. So, but I think I don't do too well. But you probably can do better than I do. So basically, like this one, I just it's not so good honestly. I guess you can massage more, then you can get better. I just have a Gaussian filter, right? So again, because I have one component here, this I call y here, y your original minus the Gaussian filter, you get the low high pass rate. Then add another image x will be the low pass. Then you put them together. Then basically that's it. So you see like this one. Okay. Oh, I need to run the whole thing. Oh, I don't know why. Maybe I should here. Okay, this is. It doesn't look too good, I would say. It's not as nice as Einstein. Can kind of see that. So I guess you guys can do a better job than I do. Yeah. So. And this is another potential. I was thinking to make a homework, but maybe not, or maybe I will. So it's like that's the. I'm not sure you can find also like OpenCV. You can find that. So this is the just the classic apple orange, and you with OpenCV after reading the image, you can just have this like pyramid down will just go down, very simple. So and then you have pyramid up is like just going up. So then.
So the pyramids are just used for upsampling, downsampling?
Yes, actually it's very nice. They already do filter. So it's like when you pyramid down, actually it's like, yeah, filter and downsampling, yeah.
But is it, I don't know what the word is, like invertible? Like?
Oh, yeah, actually not. It's not, I don't think it's a perfectly reconstruction.
Okay.
Yeah, it's not a perfect reconstruction, but it's reasonably good because as you can see, like, I don't think it's perfect reconstruction. You can see here, apparently it's got blur.
But it's better than just.
Yeah, but you of course it's better than you feels like that, right? Just put two images together, so you go. Um, yeah, but I actually I implemented MATLAB also in the past. I don't know whether like I still have that code for MATLAB. Yeah. Yeah, I have one. Oh, MATLAB is in. Okay. Let's see if like image resize. I guess I need to use a real MATLAB. I kind of remember I used MATLAB because like in the past I talked more detail with this like image pyramid, but I found typically you guys are not very interested with that detail. So oh, this is not. Oh, this is not that one, I guess. Then the hybrid MATLAB. No, I cannot find that. But I remember like my own implementation in MATLAB. I'm not sure. Just my impression is the quality is a little bit better. Depends on like how they do blurring, I guess maybe. Yeah, because if you're interested, you can. This is very easy to implement yourself also, and the original implementation is like the original paper also described this Gaussian pyramid actually do this filtering and I mean low pass filter and also like sampling at the same time. So he didn't separate that. He essentially just like if for example like I start with let's see, I start with here. From like low resolution to high resolution here. So in 1D case, so this is the high resolution to the low resolution here. So it basically just, you can think of it just a weighted sum, right? For each of these samples, it's weighted sum of this label here. It's like do a filter at the same time. And then like he tried to apply some constraint on this filter. For example, he wants it to be symmetric, right? And also he can want some of this filter to have like same energy. So same energy in the sense like if you go this way, when you go back you want to kind of like preserve the energy. So therefore like essentially when you use W0 to go up here, when you go down here you also use W0, something like that. So for example you go up here W2, you go down here also W2. And then also like when you, because you have go up and go down, actually you don't have like the same number of connection here. So then it also enforce some energy constraint. So I want this to add together is equal to 2, this one. So then eventually he can determine like the exact parameter will be like have some constraint there. So then he used this CBABC so on. And basically the number will be like this, like this ABC and only have like actually one parameter there, A there. and the parameters can be, if you change it, it can be more Gaussian-like or like more triangular-like, and actually you may even implement like this, because this essentially like when you weigh the sum. Okay, by the way, when you for example, like maybe I go back here. When you downsample, for example, I downsample here. When I weigh the sum this guy, think of actual implementation. What should I do? I have an image here. What I'm going on is say I just shift this image one at a time and then just add them together, right? So you can work on matrix at a time. The boundary is a little bit, it's okay, you just patch 0 there, right? So but you just shift like 5 times there and then you add them together. This way, like every row you do one time, then okay, I should say like one dimension you do it one time, because this filter is separable. You can do one time this and then other time this direction, then you're done. So therefore, actually, even if you don't use OpenCV, that command you implement yourself is very easy. Actually, the first time I do it, I implement it myself, and I remember actually the visually I think it's even better so than the OpenCV implementation. I'm not sure. Maybe the filter there is too strong or whatever. So, but anyway, I guess I any questions, or like, if not, I may just stop here. So,
OpenCV does have the pyramid.
yes, the pyramid, but the OpenCV pyramid function is a more, what should I say? Less control. It doesn't have much. It's very simple. So it may have some parameter. I didn't check on that. So, but basically, it's just say maybe I can try to check on that. Let's see. Pyramid down. Yeah, it has some of these. I think you can control the border, but I don't think you can control anything else. It's just control how you handle the border.
Have you posted the homework yet?
Huh?
Have you posted the homework yet?
Yeah.
Okay.
It's in Canvas.
No, it's not on page.
Oh, I didn't.
know what you said, so I was like,
Yeah, I always forgot. Like Canvas, I probably put it there, but it doesn't. It's good you remind me. Yeah.
Is he reminding you of the homework?
Huh?
What's this homework you're talking about? I was sick on Tuesday.
Wait, just the one? This one? Yeah. Yeah, it's on the. Yeah, but I actually put up on the Canvas also, but I probably didn't again. Yeah. I think I. That is the problem. Let me go there. I think it's not posted. It's published. Yeah, I always forgot this. Yeah, now it's published.
All right, thank you.
Yeah. Okay.